Okay, today we will moving to the plane problem. Before we go to the topic, we have to overview on the theory of elasticity first. Okay, first of all, I would like to focus on the stress tensor. The stress tensor notation is when we focus on the stress at a point, when we focus on a stress at a point, stress occur at a point of body. Okay, you may imagine that you have body that is subject to force system, something that is force something. Okay, and let's consider some point inside the body. Okay, if we focus the point inside of the body, for example, this point P, if we zoom out to be here. Okay, so for the point P, okay, if we consider point P like a cube, okay, that is subject to the stress, okay, surrounded, stress surrounded, and we focus on the stress on the Cartesian coordinate system first, that we familiar with. Okay, so then when we set up the coordinate system x, y, z like this, we set up the coordinate x, y, z. Okay, and we call the plane that perpendicular to the x-axis, plane that perpendicular to the x-axis. This is the plane perpendicular to the x-axis. We call this is a plane x. Okay, and also for the plane that perpendicular to the y-axis, we call this is a plane y. Okay, this is plane y. And if we focus on the plane that perpendicular to z-axis, we call plane z. Okay, for each plane, okay, for each plane is composed of stress vector. It's composed of stress vector. Okay, stress vector acting on that plane. Okay, we call the stress vector like the traction state Tx, that is acting along the plane x. In the same manner, for plane y, plane z, we have the stress vector acting along that plane. Okay, for stress vector, if we consider stress vector Px that is acting along the plane x, is composed of three components in x direction, y direction, and in z direction. Okay, so then we may call it like okay, so that this is the, we call this sigma x. Okay, x, the first subscript is mean the plane. Okay, so the stress vector along the plane x, that is sigma x vector, okay, is composed of three components, that is sigma x xi, okay, plus sigma x y j, plus sigma x c k. Okay, so then in the same manner for sigma y, that is the stress vector along the plane y. Okay, it has three components also, that is sigma y xi, okay, plus sigma y y j, okay, plus sigma y c k. Okay, and for plane c, okay, for plane c, that is sigma c, become sigma c xi plus sigma c y j plus sigma c c k. Okay, then if we write it in the metric form, we call this in the metric form like a stress tensor. like we call it like a straight tensor. Okay, tensor is the it's like the quantity in mathematics. That's the we may use to define any quantity that it has a lot of dimension. For example, like this, the straight tensor is a second order tensor. Okay, if we talking about the vector, it is a first order tensor. If we talking about the scalar, it means that it is the zero order tensor. Okay, but for the straight tensor, it is the second order tensor. This is in mathematics. Okay, so then we write it in the metric form like this. We have 9 components, right? But if we consider the equilibrium condition, we found that the straight has the symmetric case. Okay, so symmetric case, what does it mean? It means that sigma x y and sigma y x, sigma x c and sigma c x and sigma y c and sigma c y. It satisfies the condition of symmetry. That means that sigma y c equal to sigma c y, sigma c x equal to sigma x c, sigma x y equal to sigma y x. Okay, so then the state component that it actually is composed of 9 components, right? It's reduced to 9 components. It's reduced to 6 components. That is composed of the normal stress sigma x, sigma yy, sigma cc. Is the in diagonal of the stress tensor. We call this is a normal stress. Okay, and composed of sigma xy, sigma xc, and sigma yc. Okay, then we call this group. That is maybe the upper of the triangle, the upper triangle of the straight tensor, or the lower triangle of the straight tensor is the components of shear. Okay, shear stress. Okay, remind you that sigma ij, I represent plane, J represent direction. Okay, so according to this notation, it means that sigma x means it is the normal straight along the plane x. Okay, normal straight along the plane x, that is like this. This is this component. Sigma x is this component. Okay, and if we focus on sigma yc, sigma yc is sigma yy is a normal straight along y component. Is this. Okay, if we talking about sigma cc, it's the normal component. Is the straight along the plane, on the plane c and in direction c, so it is the normal straight also. But if we focus on sigma, if we focus on sigma xy, what does it mean? It means that it is the shear. It is stress along the plane x, but in y direction, so it is the shear stress. And also sigma xc, it is the straight on the plane x, but in c direction, so it is the shear stress. Okay, and so on for sigma yx, sigma yc, sigma cy, and sigma cx, the same. This is a component of shear. Okay, so this is the straight at a point in 3-dimensional. That's we have to understand. Okay, but if we focus on just only plane along, it's just we forgot just only the plane. So let's consider for the plane straight. For the plane straight that we have just only 3 components. Okay, so then the outer plane we will not consider for the plane straight that you're familiar with. That is right in this. If we consider plane XY, if we consider plane XY, the positive side convention of straight tensor for plane problem. Okay, so it's composed of sigma XX like this, right? Okay, and we have sigma XY. Okay, and it is sigma YY. Okay, and also it is same sigma XY. Actually, it is sigma YX, but according to the symmetry, we call sigma XY. Okay, so then for plane problem, it's reduced to just only 3 components. Actually, it is 4, but because of symmetry, sigma XY and sigma YX are equivalent. Okay, so then this is the positive sign convention of straight of the plane straight, right? That we familiar with for mechanics of material that we have learned. Okay, sigma YY and also sigma X. We define like this for plane. Okay, if we focus on the plane straight, we can apply the more circle technique in order to find the maximum and minimum. That is we call the principal stress. Principal stress for the definition is this what principal stress is the normal stress this is a normal stress along with the plane that has no shear. On the plane that has no shear stress. Okay, so then this is the definition of the principal stress. The principal stress is normal stress on the plane that has no shear stress. And then we found that on the plane that has no shear stress, it's become the maximum and minimum of the normal stress. Okay, that is, we can determine from the Mohr circle also. That's actually when we transform the stress to the point that we will have the shear stress on that plane. Okay, we found that it is the maximum and minimum. Okay, and the formula for principal stress actually is very easy to remember. For my technique, in my technique, I remember principal stress like this. Summation max and summation min is equal to the center of Mohr circle plus and minus radius of Mohr circle. Okay, so center of Mohr circle is the average. The center of Mohr circle is very easy to remember. This is the average normal stress. So then if we focus on the plane XY, it is equal to sigma X plus sigma Y over 2, which is the average, right? Okay, and the radius of Mohr circle, is the square root if we understand the circle. Okay, you see that the radius of Mohr circle is composed of, what is this? Okay, actually we have 2 planes, right? Okay, this is the maybe sigma X, this maybe sigma Y. Okay, so then this length is equal to sigma x minus sigma y, right? Okay, so then it means that this is the sigma x minus sigma y over 2. Okay, and this is the shear stress. So when we would like to find the radius, it is we apply the Pythagoras theorem. So then it is equal to sigma x, that is the difference in normal stress over 2 square plus shear stress. Okay, this is the r square. So then we would like to find r. So it is the square root of this term. So it's very easy to understand the Mohr circle like this. Okay, so if we understand Mohr circle, we can apply anything, any problem in mechanics of material. Okay, so then not only the principal stress, we may have to understand the maximum shear stress also. The principal stress, we apply principal stress for the problem that we consider the failure mode of the brittle material. Okay, if the brittle material such as concrete, we focus on principal stress, that is all right. Okay, it's failed along the plane of normal stress. Okay, but for the ductile material, okay, for ductile material, the failure of this type of material is maybe not depend on the principal stress. It's not fail on that plane. Okay, it's maybe the weakness of this material is due to shear. Instead, such as steel, something that we have to consider the shear failure instead of the normal stress failure. Okay, so then we have to focus on the shear stress also. And for shear stress, the maximum shear stress actually is the radius of Mohr circle. It is a radius of Mohr circle along that plane. Okay, along that plane. That is the when we would like to find the maximum shear stress, mean that if we understand Mohr circle, maximum shear stress is the radius of Mohr circle. Okay, so like soil mechanics, that's we have to focus on the shear strength of the soil instead. That is when we consider the unconfined test. Okay, unconfined test, and we like to find the shear strength of the concrete, we may apply unconfined test. And if we would like to know more than that, we have to consider the triaxial test instead. Okay, so then this is the plane problem that we have learned before. Okay, and this is some example that I include a slide in order to review yourself. Okay, I think you may review it by yourself in order to find the principal stress and the principal direction. That is the direction that we transform the plane to find the plane that has the principal stress. Okay, so I think you may review it by yourself. Okay, if we moving to the Mohr circle, you may plot like this. There's this is the text of Ferdinand Beer. Okay, but if we apply the Boresi, the text of Boresi instead, you will see that the direction of sigma xy is in downward as a positive. That is maybe different in some text, but the content is just the same. Okay, but it's may different in some textbook. That is it may be have the different advantage. Okay, so the more circle of the Morrissey notation, you see that according to the positive notation at point P, we just plot sigma xx and sigma xy directly. It's not necessary to change the point, and you see that from the Ferdinand Beer notation, you have to plot the point x with sigma x and also minus tau xy instead. That is the shear stress. Okay, so if we focus on some type of problem with the more circle, okay, with more circle, that is maybe make you more understand to this type of problem. Consider the plate. If you consider the plate subject to tension, this is the plate subject to tension. Okay, so what happened to the plate when it's subject to tension? You have the applied force P over here. Okay, when we cut off the free body diagram over here, we have the stress inside of this area. Okay, this is the plate. Okay, this is applied force P. Okay, so the stress inside of this area, okay, is equal to P over A. Okay, actually, this is the, we have to say that this is the equal to the normal force. Okay, normal force that is inside of the body. Okay, sigma is equal to N over A, but because of N equivalent to the P, which become P over A, that you familiar with. Okay, when we would like to find the stress, we have to use the internal force, not the external force, but for this case, the external force is balanced with the internal force N. So then we familiar with sigma equal to P over A. Okay, so for this case, if we focus on the point, that is, we may consider this point. Okay, if we consider this point and we write the state of stress, or the stress tensor, okay, you see that from this condition, it has only sigma xx, okay, has only sigma x. So what happened to shear? The shear stress along the plane x has no shear rate, and it has no axial force along the y direction also. It has, does it mean that sigma yy becomes 0? So if we focus on this, the stress tensor is become sigma x, and then another component is become 0. Okay, it's become 0. When we plot the Mohr circle, it means that we have sigma x over here. Okay, but shear stress is equal to 0. We have this point. Okay, and another point is what? The normal stress, another value of normal stress is 0, right? That is sigma yy equal to 0. Okay, and tau xy. So then we have the Mohr circle like this. Okay, so that means that if this is the ductile material, right? If it is the ductile material, okay, we may have to focus on the shear, the maximum shear stress also. For the Mohr circle, we found that when we rotate with 90 degrees, in the Mohr circle, we will have the point that is at this point, we have point D. Then at the point D, we have sigma x over 2, okay, and tau xy, okay, and sigma xy. And sigma xy. So then, and at this point, sigma xy is become maximum. This is the maximum value. Okay. When we rotate in Mohr circle with 90 degrees, it means that we rotate the plane just only 45 degrees. Okay, because this is the angle of 2 theta, right? According to the mechanics of material. So we have this, okay? We have this condition that at this plane, okay, at this plane, we have the shear stress, okay? So it means that we first of all we focus this plane, right? Okay, and when we rotate it to 45 degrees, it's become this plane. It's become this plane. Okay, these two plane, and it's subject to normal stress and shear stress. So then this plane is not the principal plane. This is the principal plane. The X plane is the principal plane. Okay. So according to this, we have the maximum shear along this plane. And you see that the shear max, okay, try to extension the body into the blue shape, right? Okay, and after it yield, it may be broken, okay, to like this, okay. Same as the torsion. For the case of torsion that you have learned in mechanics of material, okay, when the cylinder subject to the torque T, okay, it has the shear stress occur along the surface of the cylinder, okay. If you you may consider like the can box, that's the can, the water can. That's when you twist it, okay, you will see that it's maybe broken along the direction of 45 degrees on that, okay, because this is for the case of the cylinder subject to torque, the pure torsion, we have just only the shear stress. So what does it mean? It means that the stress tensor is become like this, normal stress, it becomes 0, right? And we have just only shear stress, that is called XY. And for another component, it's become 0 also. Okay. And when we plot the Mohr circle, we have this point. Okay. If we would like to find the principal stress, we have to rotate back to this point. Okay. So for this case, the plane that we focus on at the first, it is this plane that is in X plane. Okay. That is for this plane, it has no normal stress, but it has shear stress. So this plane is not principal stress. It's not principal plane. So then when we rotate with 45 degrees, when we rotate with 45 degrees, we will find that we will find the plane. We will find the plane that has only principal stress, that is max, okay, but it has no shear. Okay, so it means that we may starting with this plane, right? Okay, we rotate with 90 degrees in Mohr circle. Okay, we rotate with 90 degrees in Mohr circle. So then we will have the plane. Okay, that is maybe this plane. Okay, it's maybe this plane. And this is just a preview on the plane problem that you already learned in mechanics of material. One thing that I would like you to mention on the case of three-dimensional also. Okay, we normally familiar with the plane stress. We normally familiar with the plane stress that we have the stress component just only three components, that is sigma x, sigma y, sigma xy, right? Okay, so for the case of three-dimensional, you will see that it's composed of three directions, and if we focus on the plane for each plane, okay, for example, if I have the component like this, that we may have just only sigma x, okay, this is sigma x, this is sigma y, okay, and this is sigma xy, okay, and also we have sigma dc. Okay. Okay, and so on. If we have three components of normal stress, okay, for the case that we rotate and we can find that we have the principal direction already when we transform it to be this shape, that is we rotate in three-dimensional, and we found out we have the plane. This plane is the principal plane. That is, this plane has only sigma x, for example, and tau xy is become 0 for that plane. Okay, and also we have sigma c and sigma y, that on that plane is become 0. So that means that we can plot the Mohr circle in three-dimensional. That is, this point is maybe sigma 1. Okay, that is we may define sigma 1, sigma 2, and sigma 3. Sigma 1 is the maximum, absolute maximum principal stress. Okay, sigma 2 is the middle value, and sigma 3 is the minimum, is the absolute minimum principal stress. Okay, so then if we consider plane 1, 2, okay, we have sigma 1 and sigma 2. Okay, we have this circle. That is the first plane that we consider if we compare with the plane problem that we have just only three components. But if we consider the plane 2, 3, we have sigma 2, 3, like this. We have sigma 2, 3. Okay. But if we consider plane 1, 3, we have the big circle, that is sigma 1, 3. That is sigma 1, 3, right? Okay. So for this case, you see that we have the area that's the stress maybe occur, that is the shaded area over here. Okay, in three-dimensional. Okay, but if in plane it means that the stress that's possible occur, it should be along the Mohr circle, the point on the Mohr circle. Is the stress that that can be occur on that. Okay, one thing that you have to be careful, it is what is the maximum shear stress. It is the maximum shear stress. Maximum shear stress for this circle is the maximum radius of circle. That is the big one. Okay, so then the maximum shear stress is equal to this. That is the R max. Okay, shear max is equal to sigma max minus sigma min over 2. Okay, you will see that for each circle, you will have, if we consider this, you will see that this is for 1, 2 plane. Okay, these are for 2-3 plane, and actually this is for 1-3 plane. Okay. First thing that you have to mention, that is for new engineer that's familiar with that solid plane. Okay, so for some case you may found that for the plane problem that you will see, you may have the state of stress like this. You have sigma x, you have sigma xy. Sorry, you have sigma yy, and also you have sigma xy like this. When you plot the Mohr circle, you may have the Mohr circle just only one circle, right? Okay, and when you design, be careful that this is you may have sigma xx, that is the principal stress over here, and this you have sigma yy over here. So when you find the shear max, if you focus just only this plane, you will see that this plane has shear max equal to sigma x minus sigma yy over 2, right? Okay, if sigma x and sigma y is become the principal stress. Okay, but you may forget something, that actually this is not the absolute value of shear stress, because if this state of stress is not subject to the out of plane force, so it means that sigma cc is become 0, right? So then what does it mean? It means that you have another point over here. Okay, so then if we focus YC plane, we have this circle, and if we focus on XC plane, we have the big one. Okay, so the maximum shear stress for this case is not this. Okay, is equal to sigma x minus 0 over 2. Okay, that is the important thing that you have to concern. Okay, for some case you may find that you may have to find the maximum shear stress. Don't forget to include the out plane stress also for that case. Okay, before we move to the elastic equation from elasticity theory, okay, we may have to stop review a little bit for this case.